Hi everyone, my name is Xingyu, and today I will present our work in learning visible connectivity dynamics for class smoothing. This is joint work with Yufei Wang and David Held from CMU. Manipulating deformable objects have wide applications, from folding laundry to preparing food. However, these tasks are challenging for the following reasons. First, unlike a rigid object that can be represented by its 60 poles, deformable objects can have high dimensions state representation. Second, deformable objects can have infinite degrees of freedom, presenting complex dynamics. And third, due to heavy occlusion, it's hard to reason about the state of a cloth underneath its surface. So, given an image of the cloth here, how should we represent its state for manipulation? Previous method first maps an image to a latent vector, and then, combined with the action, learns a latent dynamics model that predicts the next latent state. However, such method does not apply any inductive bias and can overfit easily. Another approach directly learns the pixel dynamics model, but this approach also does not capture the physical structure of the cloth. In this work, we propose to learn a graph dynamics model. Given the observed point cloud, we first estimate the mesh of the cloth, and then learns a graph neural network dynamics that predicts the state of the cloth in the next time step. Why do we use a graph? The reason is that the cloth can be modeled by a set of points connected by springs. This gives a natural graph representation of the dynamics, and the forces applied to each particle can be modeled by different types of edges. For example, the forces applied to a particular particle include the gravity, spring force, and collision force, and these can be modeled separately. Here's an overview of our method, and I will describe each component in detail. In the first brain, given the RGBD observation, we first voxelize the point cloud, and then compute the collision edges by connecting all points that are within the radius r to each other. For each collision edge, we learn an edge prediction GN to predict whether it is also a mesh edge. The input feature on the edge is the distance between the two endpoints. We then learn a dynamics GN. The input to the node feature includes the particle position, its historic velocity, and an indicator of whether the particle is picked. The edge feature is the distance between the two endpoints. And the dynamics model then predicts acceleration for each node. Once we have the dynamics model, we play in a high-level pick-and-place action space to smooth the cloth. Given a pick point and a place point, we will first decompose them into a sequence of low-level actions, each denoting a small movement of the picked particle, and then roll out our dynamics model using these low-level actions. To plan with our dynamics model, we use a reward that computes a covered area in the top-down view of a set of spheres centered at each particle. And we greedily select the sample trajectories with the highest reward. Our dynamics model is trained in the Flex simulator wrapped in SoftG. The training data are generated from random pick and places, and the dynamics model is trained with a one-step dynamics loss. For smoothing the cloth, we use a normalized increase in covered area as an evaluation metric. And we compare other baselines and learn a pixel dynamics model, or a latent vector dynamics model, or directly learns an RGB-based policy. We first show that the estimated mesh edges are close to the ground truth at mesh edges. In simulation, our method, denoted by the blue line here, greatly outperforms all baselines on a different number of actions. Here, we show smoothing results in the real world with a Franca arm. The left is a smoothing video from the robot view. On the top right, we show scores of sample actions predicted by VCD, and on the bottom right is a rollout prediction of the best action. We show results on two types of cloth. The first one here is a cotton cloth. The second cloth here is made of silk. We can see that in both cases, the robot is able to smooth the cloth in a few pick-and-place actions. In conclusion, we propose learning a visible connectivity dynamics, which poses strong inductive bias that fits the physics of deformable objects like cloth. We show zero-shot sim-to-real transfer for cloth smoothing of different materials. For ablation studies and more videos, please check out our website and the paper. Thank you.